So I'm going to, every semester, I think I should turn this into another lecture video, and I think I'm going to now. So at some point, I'm going to chop this out of the Zoom meeting and make a new lecture video out of it. So I'm going to present it like it's one of those. Okay, so we're looking at a couple of applications of second order linear DEs. The first would be a mass on a spring. So we'll do this horizontally. I've got some mass sitting on a spring here. And right now it's at some equilibrium position. The spring is not stretched or compressed. If I then stretch the spring out from equilibrium, so X here will represent my displacement from equilibrium. Hooke's law says that a force is going to go in the opposite direction of whichever way I moved it. If I stretch it out, if X is positive, my force will push me back, negative. If I compress my mass, compress the spring, the force would push to the right. It would be positive. So Hooke's law says that there's a force, negative K times your displacement from equilibrium. Well, we know from physics, Newton's second law, F equals ma. So ma, the only force we have here in the horizontal direction, is Hooke's law, negative kx. A, though, you may have seen this notation before, those are dots. X double dot means the second derivative with respect to time. Acceleration is just the second derivative of position with respect to time. So here's our dE. That literally says ma equals the sum of our forces. We could put everything on one side. We get a linear second order homogeneous dE with constant coefficients. Like, we can solve this in general. We don't even need numbers there. We get this characteristic polynomial. We get lambda squared is some negative number, so we're going to get complex solutions. Lambda is plus or minus the square root of negative k over m. Bring that negative out as an I. And we're going to call this thing right here, this square root of k over m, we're going to call that omega. That will be our angular frequency. So our solutions are 0 plus or minus I omega. We know how to write that. We get complex solutions. We'll get e to the a and cosine and sine of b times t. E to the 0, of course, is 1. Okay, now that's a lot of math. Let's think about this dE for a minute. I've got some dE that says you take two derivatives of a function and you get the original function back, but you pick up a negative. What kind of function, when you take two derivatives, do you get the same thing back, but you pick up a negative? Sines and cosines. So that solution shouldn't surprise us. Okay, so here's our general solution. Let's do an actual example. So using these parameters, K is measured in newtons per meter here. My initial displacement from equilibrium. So I've stretched this thing out 3 centimeters, and then I'm letting it go. I'm not giving it a shove. My initial velocity will be 0. Okay, so just plugging everything in, omega square root of k over m, I get an omega 5 radians per second. Now I just need to solve for my initial conditions. So x of 0 was 0.03, cosine of 0 is 1, sine of 0 is 0. We just get a is 0.03. X prime of 0, the derivative of cosine will be negative sine. Negative sine of 0 is 0, so I don't even need that. Derivative of sine is cosine. So I get a 5b times cosine. Cosine of 0 is 1. So I skip some of the algebra here. We'll get 5b equals 0 or b equals 0. And that's always going to be the case on here. A here is always going to be your amplitude, the amount you stretched, and b is going to be some multiple of your initial velocity. So we get a graph that looks like this. Our mass is going to go back and forth. We stretched it out 3 centimeters. We let it go. We don't have any friction in this example, so the mass is just going to bounce back and forth like a cosine. Okay, you may remember from trig that the period of a cosine function is 2 pi over whatever's in front of your variable. So 2 pi over omega. So my period, the time it takes to make a complete cycle to go all the way over and back, will be 2 pi over 5 seconds. Okay, let's take it up a notch. Let's throw in some friction. So now we've got some frictional force. We call this damping. A great example of this is buildings are built with spring-like structures that have dampeners on them to help withstand earthquakes. So I've got some frictional force here, and let's assume that this frictional force points in the opposite direction of whichever direction I'm moving. So my frictional force is some negative times my velocity. If I'm moving to the right, friction would point to the left to slow me down. Remember, of course, velocity is just the first derivative of position. So the sum of my forces, I still got Hooke's law, and now I've got this frictional force. So if I write everything in terms of x, position, remember this is F equals ma. A is the second derivative, v is the first derivative. We get this dE. Again, second order, linear, homogeneous, constant coefficients. We can just solve this in general. We get our characteristic polynomial, and we can just throw that right in quadratic formula. So check the details here. I just threw it in quadratic formula. Everything's really going to depend on what happens under this radical, what happens with my discriminant. So the discriminant here, I just did a little bit of algebra. We could write that guy like this. What matters is whether that discriminant's positive, negative, or 0. Now, m is always positive, so I don't care about the bottom. Just look at that top. If that discriminant is negative, then I'm taking square roots of negatives. I have complex solutions to my characteristic polynomial. I get exponentials times sines and cosines. And we'll get some solution that looks like damped sines and cosines. So maybe something that looks like this. So we still get oscillations, but the oscillations get smaller and smaller because this alpha here is going to be a negative, so we get some decay factor times our sines and cosines. Okay, what if that discriminant equals 0? Well, then we get 2 repeated solutions to our characteristic polynomial. So we'll have a repeated root, and we'll get some solution that looks like this. We will get some lambda 1 that pops up twice. Anytime you have a repeated root, for that second function, you got to tack on an extra t or x or whatever your variable is. So we'll get a solution that looks like this, and our spring will just slowly come to a stop. We call this critically damped. Or if your initial velocity is enough, your spring might come past equilibrium and then come to a stop on the other side. So we got some spring, it's stretched out. If we just let it go, it's just going to asymptotically slow down and come to 0. If I get enough of a nudge, it might go past our equilibrium and then just slow down from the other side. But it's not going to bounce back and forth over and over. Okay, if my okay, so we did underdamped, critically damped. If my discriminant is positive, then I'm overdamped. I get two real solutions, both of which will be negative exponentials. And again, it's the exact same situation as critically damped. Critically damped is that boundary between overdamped and underdamped. In critically damped, if you reduce the friction just a tiny bit, you get oscillations. Okay, if we take it up a notch and we do some forced vibrations. So now we've got something that's forcing our mass to go back and forth. Maybe this function could be anything. It could be a constant, it could be something sinusoidal, it could be any function you can imagine. Like if we have an earthquake, that forcing function would be the earthquake itself, making our building bounce back and forth. Okay, so now we have a non-homogeneous DE. We would solve these like we do all of them. Solve our homogeneous version, get our complementary function, take a guess at what we think, our particular solution is. Then our general solution will be our complementary plus our particular. Okay, I'm going to do something similar to that in the RLC circuit, so I'm not going to do an example with springs. Okay, so let's look at an RLC circuit. So we have a resistor, an inductor, and a capacitor, and maybe a voltage source in a circuit. And we want to talk about what the current is going to be as a function of time. Okay, so I'm not going to go through all the math deriving this equation. You can look that up. But here's our starting equation, where Q is the amount of charge on the positive plate of the capacitor. And I, current, it's just the derivative of charge. It's how much charge flows per unit time. That's literally the definition of current. So if I take this dE here, and I just take the derivative with respect to time of everything, dq dt is just I. Of course, the derivative of I prime is I double prime, and so forth. Now, throughout this example, I'm using capital I. After I wrote all this up, I thought more about it and thought I really should be using lowercase I. We tend to use in a physics class capital I for a peak current or a constant current, and lowercase I for a current that changes in time. I've already written it up. I'm not rewriting. Okay, so here's our DE. This is a second order linear non-homogeneous DE. So let's solve an actual problem here. Okay, so here are my given parameters. That's an omega there. I have a resistance of 2 ohms, an inductor of 1 Henry. That's what's in inductance is measured in, and a capacitance of 0.02 farad. Actually, I think that might be a typo there. Yeah, I'm sorry about this. That should be 0.2. My capacitance is 1/5. And here are our initial conditions. We're assuming our initial current, notice here I did use lowercase I, is 0. And our initial derivative, I prime of 0, is 10 amps per second. And I'm assuming I've got some kind of voltage source that I'm slowly turning up. So my voltage is starting at 0, and I'm increasing the voltage by 10 volts per second. Okay, so here's our DE. So remember on this side, we have V prime of t. The derivative of 10t with respect to t, of course, is 10. Okay, so let's solve this non-homogeneous DE. First, we find the solution to the homogeneous version. Set this thing equal to 0. Find our characteristic polynomial. That's going to be lambda squared plus 2 lambda plus 5 equals 0. We just throw that in quadratic formula and get our two solutions. So we end up with complex solutions. So remember, when you're writing up your complex solutions, it's always going to be an exponential with the real part as your parameter, and then sines and cosines with the imaginary part as your parameter. And of course, our variable is t. Okay, now a common mistake people like to make here is they like to now take this guy and throw in their initial conditions and solve for A and B. You can't do that yet. You have to get the entire general solution, including the particular solution, then find your constants using your initial values. So what about our particular solution? Well, on the right, I just have a constant. So let's try it. Let's see if, take a guess, assume our particular solution is just a constant. Well, then both derivatives, first and second, are 0. Then plugging that into my DE, I assume that I was just a constant C, 0, 0, 5C equals 10. So C must be 2. Then my general solution, the complementary function plus that particular solution, there's the plus 2. Now I throw in my initial conditions. And again, you can check all these details on your own. But if I plug in a 0, sine of 0 is 0, cosine of 0 is 1, e to the 0 is 1. I'm going to get a plus 2 equals 0. So a is negative 2. And then for the derivative, I've got a product here and a product here. I'm going to have to use product rule to find my derivative. I get this. Plugging 0, all the signs are 0. Cosine of 0 is 1. E to the 0 is 1. We get this equation, which gives us b equals 12. And then here's our particular, or our solution to our IVP. And then here's what the graph of that looks like. So our current as a function of time starts at 0, it spikes up, and then it eventually levels off. This does keep oscillating, we just can't see it, but it asymptotically decreases toward this equilibrium current of 2 amps. And we could make this more complicated. We could, if we wanted to, maybe over here, make this voltage source sinusoidal in nature. Throw in a sine or a cosine there. Then we'd have to take the derivative of that, get some other sine or cosine, and then we'd end up with a much more complicated current. Okay, I think that should be good for today. Make sure you study well for the test. Again, you're not allowed to use any kind of outside resources. Don't use Chegg, don't use Photomath or anything like that. Make sure you show all relevant work on your written solutions, because that's what I'll be grading more than what you type in. Stop the recording.